Okay, we're on the air again. Last time I stopped here, last part of chapter 6, which was on election algorithms. I think this will take me about 15, maybe 20 minutes to discuss. It's not really that much of a big deal. As I've mentioned now a couple of times, what you often see in distributed systems is that the best solution is the one which is coordinated. Okay? And this happens over and over again. And what you often need is you can statically pinpoint who's going to be the coordinator all the time. Then you could really talk about a centralized solution. But in many cases, even when the coordinator fails, you'll have to find another one. And this is done by means of election algorithms. So the whole idea is that we're going to look at an algorithm that requires a process to act as a coordinator, and the question is how to select one dynamically. I think I've made this point quite often now. The coordinator can be chosen by hand, in which case you have a single point of failure, but okay, maybe that's even better than having endpoints of failure. Now let me just pose these two questions directly. If a coordinator is chosen dynamically, do we have a centralized or a decentralized or a distributed solution? It's more centralized versus non-centralized. That after 2 minutes. Yes?
Can be both, I think.
Can be both? Okay.
The selection of the coordinator part is centralized, and then afterwards can be centralized.
So here's the situation. I have a distributed algorithm, or system, it really doesn't matter. It has a coordinator. If the coordinator fails, I have a mechanism to dynamically choose another coordinator. Do I have a centralized or a non-centralized solution?
I would argue that it's more on the side of decentralized, because when failing a coordinator, then we dynamically, randomly choose another one.
Mm-hmm.
The other one has to know where to continue from the failing one. At least not to sense the difference that a lot of data is stated on.
Okay, so let me try to rephrase what you said. You argue that it's more decentralized because if you hand it over, then the new coordinator will have to pick up where the other one left off, as much as it can. Okay. Anyone in favor of a centralized? Yeah, go ahead.
So in my opinion, it can be both, depending on the election algorithm you choose.
Okay.
The election algorithm is started by a single person, in that case centralized. If the algorithm is started by multiple processes, it's decentralized.
Okay, so depending on the election algorithm, if it's, I'm repeating because of the recording, if there's a central single node starting the election, it's centralized, and otherwise it's decentralized. Any other opinions? Yes.
I think the main difference lies in fault tolerance. If you can, if the leader, the coordinator crashes, and you can recover by simply collecting another coordinator and continue, then I would say it is a decentralized solution because you do not rely on the center being up all the time. And if that's not the case, it's just like, setting up a server and installing software and say, well, this is the coordinator for all time.
Okay, so you make the distinction between a more or less a static solution, which would then definitely be centralized, and a non-static solution, which you would argue will be decentralized. Okay, let's hear one more opinion.
Well, it has to be decentralized, and it kind of is what is implemented in Skype, which you deemed a decentralized system. Skype, where these hub nodes, manager nodes are elected depending on how long they're online and stuff. Then they are like promoted, and if that is a decentralized system, anything that works along those lines should be a decentralized system as well.
Okay, so this is an interesting observation. If you take a look at Skype, which is declared to be decentralized, which has hubs and stuff like that, then if that's the criterion, then no, basically you're saying let's use that as a criterion and decide whether something is centralized or decentralized. The interesting thing about Skype, by the way, is that it has a central component, namely the database where you first have to log in and then it spreads the news. So I could argue, well, is Skype then a centralized or a decentralized solution? The interesting thing is it actually an interesting question? Being centralized or non-centralized? I would say, well, it kind of depends. But the real thing that, of course, we're interested in is which solution would be better. And personally, I don't care whether it's centralized, decentralized, distributed, non-centralized, a combination like in Skype, I'm more interested in other aspects like how robust is it? Does it have a single point of failure? Does it have endpoints of failure? So to come back to come at least to the other question, is a fully distributed solution better always? No, definitely not. We saw a couple of cases there, like the nicely fully distributed mutual exclusion. Thank you very much. I just introduced endpoints of failure, and I don't know, whether you would actually, if you would have a floating coordinator, whether you would call that centralized or not. And actually, I don't really care. Yes?
So basically the right question would be, does it work?
Would the right question be, does it work? I don't think the criterion, does it work, would be good enough. Because many things that seem to work are really heavily flawed until you bump into really fundamental problems. And just being in a state that it works is, in many cases, really not good enough. But in this case, I think the question was wrong, because what you could have asked me is, what are you really asking? Is one better than the other? And then better could be under which circumstances? Does one perform better than the other? Okay, maybe, under which circumstances? Is it more robust than the other? These are the relevant questions, not whether you would call it centralized or non-centralized. That will be my argument. Don't worry, this would never be a question for an exam. Okay? But let's take a look at an election algorithm. And one that is kind of simple is simply bullying. And what you do is you assume that you have a bunch of processes, and they all have each has an associated unique weight. And then what you do is you try to make sure that the process with the highest priority or weight will actually be elected as coordinator. The issue is, how do we find the heaviest process? Well, there are different ways of doing it. I think there's actually a scheme over here. I'm not quite sure whether I would actually do it like this anyway, nowadays. Here you have a bunch of processes, and let's assume that 7 just crashed. Okay? And then 4 starts an election, say, hey guys, let's vote. I'm not original in that sense. And then 5 and 6, they return an okay, but both cases, 5 and 6, have a higher priority than 4. And I'm just taking the process ID as their weight. And then they continue their election, trying to also talk to 7, but 7 has crashed, and 5 sends something to 6 and also to 7, and in the end 6 will say okay, and then 6 eventually becomes the coordinator. Okay, that's bullying.
Okay here means you lose the election.
Yeah, you use the election. Can you just come up with another possible solution? Yep. Gossiping, exactly. Who cares? Just float around what your maximum number is, Uh, when will you decide that you're the one that won?
After a number of steps, I mean, login, and all them.
Oh, after a number of steps.
Or when you receive any messages from the other nodes, some acknowledgement that you are the one.
An acknowledgement that you're the one, okay?
It changes constantly, so it doesn't really matter if you are the only one at that moment, but as long as you don't receive a message that somebody else has a higher number, you are the one.
And then what? So I have to repeat this. So you just assume you already have the highest one until somebody overrules you, and then yes, but then what? But it means that the coordinator does things, right? So I just start to coordinate, but I'm really not supposed to coordinate because somebody else may take over that role. Is that a problem? Right, you can't act if you do not receive a message. But here the suggestion is, who cares, just act.
You might be ruining the system before you get a response from somebody else who actually should and has also started the process. You know, the state of the third parties.
Yeah, so let me try to rephrase a bit what you just said. You may be ruining the system. Because it was really not supposed to happen that you could have two coordinators at the same time. Now this is actually the crux of the matter, and the reason why I'm emphasizing this a bit is that yes, I believe you're right. You should just start acting as a coordinator. What you need to do when you design such a system that should rely on gossiping and then just start doing your work, is that even if you have two coordinators, having two coordinators will not do damage to the system. So for example, one that will not work is when you're a coordinator for handing out OKs for accessing a file. Okay? So you will have to design your coordination function such that somebody else can also be coordinator and overrule you without you having ruined the system, to quote you. So that really kind of depends. Designing distributed systems such that you can have multiple coordinators, that's a challenge. And in general, if you can manage to do so, you will have a very robust system where you just start gossiping to see who should be the coordinator, and in the meantime, people are just coordinating without ruining the system. I think that's actually what designing distributed systems is all about. If you can't have that, you will have to wait until the election is done. And in a very large distributed system, that's not what you want. Okay. Here's another one, a simple one, election in a ring. You assume everybody's organized in a ring. No, not 10,000 processes. A handful, 10, 20, something like that. And you start basically circulating a token along the ring to find out the process with the highest priority. So basically, your election goes through the ring, around the ring, and then after it has been passed through everybody at least once, you know exactly who the coordinator should be, and you pass it around. Okay? Yes?
If you have another node added to the network, then
So this will work in a static ring. It will even work in a static ring where two processes at the same time start an election, and you will have to take special measures if nodes are allowed to join and leave the ring. Of course, they will leave the ring because this is the reason why you started the election, because then you will have to skip that node. Joining is a bit more tricky. As soon as a node joins the ring, what you will need to do is instantly start a new election. Okay, but it's basically all the same. And that's, we just answered these two questions. Does it matter if two processes initiate an election? Nope. And what happens if a process crashes during the election? You just start again. Okay. Now this one is kind of nice actually. So now let's get back into peer-to-peer mode, and we want to elect super peers. For example, this could happen in the Skype network. But just imagine we have a kind of a completely flat peer-to-peer network, and I want to designate special nodes to do special things like indexing stuff. Okay? So let's assume that normal nodes have low latency access to super peers. Super peers are evenly distributed across the overlay network. Yes, this is what we want. There is a predefined fraction of super peers, and each super peer should not need to serve more than a fixed number of normal nodes. And what you can do, it's really simple actually. You simply reserve a fixed part of your identifier space for super peers. Okay? And then if you want to have S super peers, you take K is the ceiling of log to S bits of your identifier space, and you reserve those for the super peers. And if you then have n nodes, you'll have on average 2 to the power k minus m. M was the number of bits that you use for your identifier space times n super peers. And what you do is when you want to route a message to a super peer, you simply take this key P. Okay, this was, for example, the key associated with a file, and then you simply route it to the node responsible for P and this one. And this one has exactly k bits, and now you know that it will be routed to that designated peer. That, just by coincidence, happens to be your super peer. Is this clear to everyone? The picture that you should have is, I have an overlay network, a super peer overlay network, and I want to designate a certain fraction of those nodes as super peers. And the question is, how do I designate those guys? Well, you just reserve a part of the identifier space for that, and not by specific identifiers. No, just take the k leftmost bits. Okay? And if you want to route to such a super peer, you take a key, you AND it by taking a bit mask with the first k bits equal to n, to 1, and that means you will automatically be routed to the super peer responsible for that part of the identifier space that you have in your key, full stop. And this works under the assumption of a uniform distribution of super peers over the super peer network. And by that I mean that you had a uniformly at random draw from this huge identifier space for every identifier that you will use in the peer-to-peer network. Yes? That's as simple as it gets. Okay.